Hello and welcome back to another CMIS 468 video follow-up because everybody was getting tired in class, including me. There was one last topic that we didn't get a chance to talk about in class, and that's software-defined networking. It's an important concept, and I would have done you a disservice to try to get into it when everybody's already feeling tired, because this is one of the most advanced things in this entire course. All I can do is give you an introduction to the concept because really you're not going to be in a role as soon as you get out of college. Even if you're a network administrator, network engineer, network architect, you're probably not going to be doing a lot with software defined networking immediately. However, it will make you sound like a smarty pants if you can at least mention in a job interview that you've been exposed to this idea. It'd be a great question to ask, but only with a large employer, like large employer, to ask them if they're doing anything with software-defined networking. It would make you sound smart. So if you read like a Wikipedia article on software-defined networking, I think you're going to get confused quickly because it uses terminology like managing network services through abstraction of lower-level functionality. Um, so this gets pretty strange pretty quickly. In order to really dive into this topic, let's back up and go back to the study guide for the first exam, where one of the questions some people asked me about was what's a forwarding decision. I had that question on the study guide for the first exam, and some people said they're having trouble finding it in the book. And I think the easiest way to think of a forwarding decision is every piece of network gear has to make a forwarding decision. Some message comes in, whether it's a frame or a packet, it has to look at it and decide where it's going to go next. It has to forward it. So it's going to look at the destination address. We forward packets based on destination addresses. We forward frames based on destination addresses. We forward segments at layer 4 based on port addresses. So they all have forwarding decisions to make. Now, what's interesting is that's a little simplistic because there's something else going on. If we look at this slide from the book, that there are two things happening. One is a forwarding decision, and one's a control decision. If you want to think of the forwarding decision as how to forward the packet out, by address. Which interface does it need to go, if it's going to go over to this network, where's my hand? There's my hand. Which, which interface on the router is it going to go out? The control decision has to do with whether you should even forward the packet at all. Is this an important packet? Because some firewalls and routers can do some pretty sophisticated packet shaping where they decide, based on quality of service metrics, whether that packet should in fact go through, or whether it should go out later, or whether it should go out a slower circuit. Those kind of decisions based on more intelligence built into the box are control decisions. So a forwarding decision can actually be broken up into forwarding information and control information. Now, wouldn't it be interesting if we could tear those two things apart? And that's what we're getting into on this slide. With traditional switches, routers, access points, forwarding and control are kind of merged on the same box. So there's a lot of redundancy in a way. If this box is having to make decisions, and this box is making decisions, and this box is making decisions, wouldn't it be great if we could centralize that process instead of having to update this box, update this box, update this box? And when I say this box, I mean thousands of these boxes, right, on a large network. Wouldn't it be great if we didn't have to do it one at a time? Well, the simple idea behind software-defined networking is abstracting the control function out of just the mechanics of how to forward messages around. So if we abstract out this control function and have one SDN controller box that's sending commands to all of our boxes throughout the network, so all they have to do is forward, 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 which is a lot faster, right? Making a forwarding decision is a lot faster than a control decision. So management, which is the topic of this chapter, becomes a little more streamlined if we can centralize. to know why this is happening now, keep in mind this only applies to very, very large data centers. Google cares about this. Facebook cares about this. IBM. It would have to be an incredibly large manufacturing or retail environment with an incredibly large data center that would get into this stuff. But the history here is we've done a lot over the last 10 years with server and PC virtualization, which has allowed us to centralize a lot of server resources to well, save on energy and lower management costs and lower hardware costs. Storage virtualization over the last 10 years has also allowed us to centralize a lot of storage management so that you can string together a bunch of hard drives together in a storage area network, and the control function is abstracted. So there's one SAN controller that's providing access to many, many servers to just a big pool of hard drives, as opposed to having hard drives dedicated to each individual server. It makes sense to have a shared pool of resources. So whether that shared pool of resources are servers up here, or a shared pool of hard drives for storage, the next step in our architectural evolution is centralizing a shared pool of network resources. Again, for very large data centers, you can imagine if you have a large data center and you've got some routers that are kind of sitting there not as busy as other routers, so that's an unused resource, or firewalls that aren't being used all the time, especially access points. So there's a lot of, again, for large data centers, there's a cost reduction angle that's always going to be driving this. And then the agility argument is interesting too, because I like this part, that each individual device is changed instantly. Like if you, let's say you make one rule that, okay, during these hours, during this time of day, I want this traffic to have a lower priority and give this other traffic a higher priority, but just at this time of day, or just when this threshold is reached, I want you to make a change throughout the network. That would almost be impossible without some kind of SDN architecture in place. You would just have to go through and reconfigure each box one at a time. So the big so what, why this is cool, it allows you to do traffic shaping, not just from one box's perspective, traffic shaping across the entire enterprise, based on what's the most important thing in this entire chapter? The big theme. It's always based on the business requirements. So as business requirements change, your network can be flexible enough, agile enough to adjust on the fly without as much manual intervention on the part of the network administrator. There is a great YouTube video on this, but it's a little long, maybe 20-25 minutes. And the guy is very enthusiastic about SDN, but he gives you kind of what I've given you in 6 or 7 minutes. He gives it to you a little more slowly and methodically. It's a good explanation if this helps you out. But I'm not going to show it here. I'll let you watch that on your own time. That's what I wanted to say about software-defined networking. Maybe I could have said this in class, in 10 minutes or so, but like I said, I could feel I was losing everybody. So, when the energy goes down to the room, I take pity on you. I will see you Tuesday night in class. Looking forward to it. See you then. Bye-bye.